So today we will start topic process synchronization. We already discussed it in the process part when we discussed process cycle and all, and where we discussed cooperating processes, right? You already heard this term cooperating processes. So this is why we are writing this term under process synchronization, because we need process synchronization only in case where processes are cooperating in nature or concurrent in nature. Otherwise you don't need any process synchronization. What it means process synchronization, why you are doing this? See, if you are sharing some variable among multiple processes at the same time, that means you need to synchronize, right? For example, see who are the cooperating processes which share something, right? At the same time, which share something or which are affected by each other, right? So let's say if P1 and P2 P2 are sharing some resource are are at the same time, right? That means those two require this resource for completion of its task, like completion of its job, right? P1 and P2 both requires our resource at the same time. That means if any due to any reason, if both axes are at the same time, there may be conflict case, right? The result will be conflicted, right? So at this scenario where some two or more than two processes share some common variable or common resource, then we need to synchronize processes among each other via some mechanism, right? So in this topic we will understand then that how process synchronization took place at the time when two processes are sharing some resources, and why it is needed. Why it is needed, we will cover it by using some example, right? So cooperating processes are one that affect or be affected by other processes, right? If P1 and P2, if we are saying P1 and P2 are cooperating process, that means they both are affected by each other, by activity of each other. That means they have dependency among each other's activity, right? Here the dependency lies on resource R, right? So whenever there are cooperating processes, that means they are affecting each others, or or they are sharing some address, sharing some logical address space or file space, code or data or file. In that case, there may be the chance that this uh, this transaction or this combined form of transaction group of transactions lead to may lead to data inconsistency, right? Or we can address it data inconsistency. So we already understood it by one example. in the last class, where we took an example of account number and all, where we understood the data inconsistency method, result of data inconsistency, and what is the problem if it happens, right? So, we don't want data inconsistency in the system, right? And why it is happening? Because we are having cooperating processes in the system, and if they are cooperating, that means they are affecting each other's, right? And they are sharing logical space, address space, or code data or file. And in this case, when they are sharing some logical address space, at the same time, if they want to access, or they are altering any shared variable, that may lead to data inconsistency. So we don't want any data inconsistency, because if data inconsistency is there, then the resultant output of the processes may be corrupted or unstable, right? And we only need stable results, right? We need stable means we need only one value for x variable. If x is a common variable, then we need only one value, one updated value for all for all processes which are going to read this value, right, or change this. So we don't want data inconsistency. So to remove this type of data inconsistency, what we can do, we can ensure orderly, or in another term, sequential execution of execution of cooperating cooperating processes. So if we somehow ensure the sequential execution of cooperating process, that may lead to remove data inconsistency. Okay, right? To remove data inconsistency, we must ensure orderly or sequential execution of cooperating process. By doing this, we can ensure that there will be no data inconsistency. That means there will be no conflicted results, and the system reading and writing by any processes will be stable, right? Okay, so now, why this is happening, let us let us understand it first. Using race condition, using race condition, and we will understand the race condition by our most common or well-known problem called producer consumer problem. So what is race condition? Race condition is when two or more processes or entities are fighting or running after each other to update or to work upon any common variable, right? That means to in the C above, here two processes P1 and P2 are competing for resource R, right? At the same time, they want to alter its value, right? Let's say its value is currently its value is R value is 5, and they want to alter it, like P1 want to plus it, and P2 want to minus it at the same time. And if this happen at the same time, they want to update the value of R. That means they both are in race condition, right? That means race condition means they are racing. There is racing in between them to update or to modify any common variable between them, right? So this is race condition. Let us understand it very clearly by using an example. And here our example is producer consumer problem. So what producer consumer problem is? That means there is two process. One is producer and one is consumer, and they are sharing this buffer part. And what it says that producer task is to produce item into the buffer. And what is the task of consumer process? It is the task of consumer process will to consume items from buffer, right? So it's a simple problem. It's not a rocket science. Producer will produce the item and consumer will consume the item. But the problem will occur once this this buffer will be either full or empty. In both cases, there will be problem. In full cases, there will be overflow from producer side, and in case of emptiness, there will be underflow from consumer side. Right. So this is the problem we are stating here. We are discussing here, and by this example, by this problem, we can understand what is the race condition, right? Okay. Let us create pseudocode. Let us see the pseudocode of producer and consumer process. After that only you will understand what is happening in the system and how these two processes are in race condition, right? So this is pseudocode, not exact code. This is only pseudocode, or you can, in general term, you can say algorithm. So let us check for producer part. While true, while producer has counter, while counter equals to buffer size, right? That means buffer in equals to next produced. In equals to in plus 1 modulo buffer size. Quant counter plus plus and this one. So this is the code for producer process, where it is checking that the value of counter is equals to buffer size or not. If it equals to buffer size, then it will do something or it will not do something. And this will understand. Let's understand first what it is doing in while condition, right? Check the while statement, where it is checking the condition for counter equals to buffer size. And what it is doing, it is simply doing spin lock here, right? We will discuss it later. After checking this, uh, if this condition detected false, then what it will do, it will simply produce an item and increment the index pointer and again increment the counter, right? This will work like that. Now come to the consumer process part. While consumer will check emptiness, right, equals to 0. Next, consumed equals to buffer out, and out equals to out plus 1 modulo buffer size, and counter minus minus. So before going to understand this code, we are addressing this code here, because we only need where the producer and consumer are sharing some variable, right? So in the producer code there is in, and this is its local variable. Similarly, in the consumer part there is out, so this is not shared, right? So here what we are sharing, what the producer and consumer process both are sharing, is our counterpart. They both are sharing counter variable. When accessing buffer, it is working on counter. Both are working on counter, right? So let us understand what is happening underneath for this statement. For this statement, we are not discussing complete instructions, because it is a pseudo code, and we already know the basic working principle of producer consumer problem. But what we are discussing, we are discussing race condition here, right? So the both producer and consumer are sharing counter, right? So for this statement, for statement number 6, we are sharing both are sharing a minute, both are sharing this one, counter, right? What it means, that means it is a shared variable. And if it is a shared variable, that means there will be some conflicts whenever we are performing these, we are executing two these two statements at the same time. So what will happen, right? What will happen if both, see, if both are, if producer and consumer both access counter concurrently, then what will happen, right? And we are assuming that the value of counter, see, consumer want to decrement it and producer want to increment it, and current value before accessing the value of counter is given 5, let's say, right? So if both the process, consumer and producer, will execute this instruction number 6, this instruction concurrently, then the problem, how the problem will arose, let us see. So you all already understood, you all already studied uh, computer architecture. So let's understand first what will happen in this case, right? So for counter plus plus, what what is really happening underneath in the system, there will be some register, let's say register number 1, where you store counter, right? After that you just increment register 1 by 1 register 1 plus 1, and after increment you will simply update value of counter with register 1, right? So at the lower level, these three statements will run for this single counter plus plus, right? In the same way, for counter minus minus, for counter minus minus, what is happening underneath? Let's say consumer is using register number 2, let's say, for counter, right? Now what it will do, register 2 equals to register 2 plus 1, and last counter equals to register number 2, right? So these three statements will be executed for single statement given for counter minus minus, and similar in the same way for counter plus plus, right? So here in these here in both the cases, register 1 and register 2 are local register or local registers, we can say accumulators, right? And all the values are which are going to save or restored is done by totally interrupt handler, right? We already I think we already know it, that value saved and restored by interrupt handler. Interrupt handler, right? So these there are three transactions which will take place, right? Transaction 1, let's say transaction 1, transaction 2, transaction 3, for this and for this, right? These are respective transaction 1, transaction 2, and transaction 3 for consumer and producer process, right? Let us understand it by sequence of execution. Let's see, let's assume, let's see, transactions took place in the order process steps. Okay, let us take an example where P for producer and C for consumer, right? Let, let's assume that transaction number T, first producer process will execute transaction number T0 and T1. Okay, let's rename it. It is T0, T1, and T2. First producer will execute T0 and T1. That means register 1 will be equals to counter. Counter means value will be 5, and after that transaction number 1 of producer will be executed, let's say. Then register 1 equals to register 1 plus 1, that means it will be incremented by 1, that means it will be 6. Now the register 1 value will be 6. Okay, now we assume that after two transactions of producer process, next two transactions of consumer will take place, right? So T0 and T1, T0 and T1, T0 and T1 for consumer process. Register 2 equals to counter, that means 5. Still counter value is not updated. Both processes, consumer and producer, read counter value 5 and stored into the local register, right? And then performed alternation to that particular value. Now in the T1 transaction, register 2 will be decremented by 1, that means it will reflect the value 4, right? After that that we assume that T3 of producer process will be executed, that means counter equals to register 1, that will signify the value of counter as 6, point number 1. And in the last we assume that transaction 3 of consumer process will be executed, that means counter equals to register 2, that means it will signify the value of counter as 4, this will 2. So after these transactions, let's say this is happening time at time t0, this is happening at time, let us signify it by small t, time t0, time t1, time t2, time t3, time t4, time t5, time t6. Okay, so after time t5, when the system want to save the value for counter, then it will be confused, right? At the time t6, when system want to save value of counter, what it will find two values for the same variable, right? It will find two values for the same variable counter. One is 4 by consumer process and one is 6 by producer process. So these two results are inconsistent. That's why the system will confused, right? The system will get confused if it reads both the values for same variable counter, right? It is having two values for same variable counter, one is 4, one is 6. So totally it is dependent, that means there is will be inconsistency. And why there is inconsistency? First, there are two results for the same variable, right? And second, when the system is going to save the value, it will save the value of the counter which it will read first. For example, if the system reads value of counter 6 first before 4, that means it will update counter value as 6, right? This will be okay for process, this will be okay for process, but will be not okay for consumer process, right? Because consumers have updated the value for counter as 4, so this will be conflicted result for consumer process. In the same way, if the system save counter as a value of counter as a 4, then it will be okay for consumer process, but it will not okay for process. That means the state of the whole system of the system will be inconsistent, right? So why this is happening? Because they both are updating the shared variable at the same time. That means they are fighting, that producer and consumer both are fighting fighting to update a common variable, which is here counter, right? So therefore, a situation like this where several processes accesses this common variable and manipulate the data concurrently at the same time, right? At the same time, concurrently, an outcome of execution, and the result of execution depends on the order of in which the access takes place, right? That means the result is dependent on the out sequential order of transactions taken place or access takes place, and this is all called a race condition, where both process or multiple processes are accessing or trying to manipulate the results, manipulate the common variable. Like in our case, it is counter. The producer and consumer both are trying to update counter at the same time, and the result is totally dependent on the order of execution or order of access to the count, is called race condition, right? Okay, so this order of transactions will define the result. That means result is totally dependent on the order of execution of those independent transactions performed over a shared variable, right? So this is called race condition, right? So to avoid this type of race condition, so to avoid this race condition, we must we must ensure only one process at a time can manipulate shared variable variable like counter. So to avoid this race condition, we want that only one process at a time can manipulate this shared variable. Both process cannot do that. So we need for that for ensuring this thing, we need process synchronization, or sometimes called coordination. coordination. That's the reason to avoid this type of inconsistency or to avoid race condition, we need process synchronization or process coordination concept, right? So for that, we have the concept of critical section. So what is the critical section here? It is critical section here is really here for these two processes. This statement is critical section. This statement is critical section, right? So we will cover it in the next lecture. So till for for today, I think it is sufficient, and for today it is all. What is we understood what is process synchronization, what is race condition, why we need to avoid race condition. We understood by producer consumer problem by using its pseudocode and its code, hardware level code, and after that we created some example transactions order, and according to those order we what we found that there are two results for the same variable, and this will be the conflicted condition. That is this is what we are calling it data inconsistency. So to and we don't want data inconsistency in the system. That's why we need to ensure that there will be single result for the shared variable, right? And for that we must ensure to avoid race condition, right? And to avoid race condition we need to ensure that only one process at a time can manipulate the variable, means mutual exclusion among processes, cooperating processes, right? So avoiding race condition needs process synchronization. So that's the reason we need process synchronization when we are dealing with cooperating processes, right? So that's all for the day, guys. Hope you understood it.